Okay, good morning, friends. Okay, today we continue with the second order derivatives. Second order derivatives. Okay, so we have a look at the derivation of formulas first. Okay, since what we want is the second order derivatives, okay, this one, f double prime. Okay, so we are still using the equation from the first derivative. Okay, the equation number 5 and number 2 under the derivation of formulas of first order. Okay, so that equation number 5 and number 2, we are using these few. Okay, it's 1, 2, and 5. Okay, we want to cancel out the f prime. Okay, because we want the formula to have f double prime. Okay, we want the formula to have f double prime without the f prime. Okay, we don't want to have any f prime here, so we cancel out. Okay, to cancel out the f prime term, okay, this is 2hf prime. This is hf prime. So we need to multiply a 2 to this series so that we can cancel out the f prime term. Okay, so we use this equation 5 minus 2 times equation number 2. Okay, with the aim to cancel out this term. Okay, and then after that we have the term of f double prime with all this f. Okay, f. Okay, so this is the formula. Okay, for first order, forward difference approximation. Okay, second order forward difference approximation. Okay, so when we replace h by negative h in the equation number 10, this one number 10. Okay, after we replace, we get this, then we can get the f double prime equation, and this will be backward difference approximation for the second derivatives. Okay, so actually it's just the manipulation on the series to get what we want. We want f double prime, so we need to find a way to cancel out the f term. Okay, then we will get what we want. Okay, so this is for center difference approximation. So to get the height accuracy forward difference approximation, okay, we make use of the formula from this. Okay, then we cancel out this one. Okay, this one you can try if you want to know how to get the formula of this three. Okay, these are the instructions on how to get the formula. Okay, so these are the formulas. Okay, you have forward difference approximation, backward centered. Okay, this is for second order derivatives. So plus the first order derivatives, altogether you have 12. You have 12 formulas, okay, which will be given in the appendix. Okay, so you have to know which one to use. These are the high accuracy, forward, backward, and centered difference approximation. Okay, now we look at the first example. Use centered difference approximation, okay, to estimate this one for second derivative. Okay, so you have to know first derivative or second derivative that you need to find, because formulas are different. Okay, this is for second derivative. That means f double prime. You need to find for f double prime where x is 0.5. Okay, so f double prime 0.5. Okay, and with a step size of 0.25. Okay, next find the true value. To get the true value, that means you need to differentiate this one twice and substitute x by 0.5 to get the true value. And to get the percent relative error, you use true value minus approximation, and then divided by approximation times 100%. Okay. Now we look at this centered difference approximation. This is the formula. Okay, for second order centered difference approximation. So as what you can see here, what we need is the current 1 point after 1 point before. Okay, this is 1 point before, 1 point after. So our current x is what you need to estimate, this one. Okay, this is the current x. The 0.5, 1 point before will be 0.25 because the h is 0.25. Okay, so 0.5, 1 point before, 0.25. 1 point after, 0.75. Okay, so you need these 3 points because you need it for this formula. And after that, you just substitute these 3 values into the function to get their corresponding f values. Okay, then you substitute this into the formula and compute, you get the approximation. Okay, and for the true value, we just differentiate this one twice. You differentiate this one, this fx, one time, you get f prime. Differentiate once again, you get f double prime. Okay, this one should be f double prime. Like what? So when you substitute 0.5 into this, you get this one. So this is the true value. So to compute for the percentage of relative error, we use true value minus the approximation. This is the approximation. Okay, you give the modulus divided by the modulus of true value. Then multiply 100%. Okay, so the percent of relative error is 2.39. Okay, so are you able to understand the flow of this question, this example? Okay, next one, we look at the example number 2. Given a data set, a few data set points, we need to compute for this f double prime 4. Okay, f double prime 4. This is the current x with step size of 1. Okay, by using forward and backward difference approximation. Okay, that means the first 2 formulas and center difference approximation, h squared. That means this is the third formula. Okay, so if we look at the list of the formula, this one, the first, second, and third, you need current, next point, next 2 points. Current, 1 point before, 2 points before. Okay, so we need 5 points. We need 5 points for that 3 formulas. Okay, so you compute for that 5 points, the current value is t. With h is 1, so 1 point before is 3, and 2 points before is 2. Okay, so next one is 5, next is 6, because h is 1. After that, substitute all these values into the function. No function is given. You just take the values. Okay, you just take the needed values. Okay, 2, 3, 4, 5, 6. So that means we need this 2, 3, 4, 5, 6. This few corresponding f values. Okay, then this is the formula for the forward difference approximation. Okay, so the current will be 4. Current will be 4. This will be 5. This will be 6. Then you substitute these 3 values into the formula, you get this. H is 1. Then you can get the approximation. Okay. Then the backward difference approximation, this is the formula. We have the current 2 points before. So what we use, 4, 3, 2. This is 4, this is 3, this is 2. And you get their corresponding values, put them into the formula, you get the estimation. Okay, and the last one, standard difference approximation. This is the formula. Okay, so current, next point, previous point. Okay, so this is 4, this is 5, this is 3. You take the corresponding f values, put them into the formula. H is 1, then you get the approximation. Basically, this is same exactly as what you have learned on Tuesday. It's just that now we have different formulas because this is second order now. Okay. Now example number 3. Example number 3. Use high accuracy difference approximation. Okay, that means we have to use the formula number 456. Okay, 456 to estimate the second derivative of this at t equals to 0.5. okay, with a step size of 0.1. Okay, so this means 0.5 is the current point, okay? And if you look at the list of formulas, this one, current, next 3 points, current, 3 points before. Okay, this is 2 points, 2 points. So altogether, we need how many points? 7. Current, next 3, and previous 3, 7 points, right? Okay, so current, next 3, previous 3, with a step size of 0.1. So you have to come up with all these points, okay, in a table form. Then we will start with the forward difference, high accuracy forward difference. Okay, so this is the formula. So you just substitute the corresponding values into the formula. Then you will get this. Okay, so this is current, next point, next 2, next 3 points. Okay, where you have already got the values. Current, next 1, next 2, next 3 points. Take these F values. Okay, put them into the formula and get the approximation. Okay, same goes to the backward and centered. So if you understand the concept, this one you should be understand this how we get the approximation by using the formulas. Any questions? Any questions? Okay, now we try this exercise. Okay, given a function, use forward, backward difference approximation and centered difference approximation. Okay, that means this is first three formulas to approximate this one with a step size of 0.1. Okay, you are given the true value, then you need to compute the percent relative error for each of the 3 methods. X is 0.7, H is 0.1. Okay, and we need the first 3 formulas. Okay, we look at the first 3 formulas. Okay, how many points do you need? 5. Okay, so you compute the table. Okay, for 2 points and 2 points before and 2 points after. And the current value is 0.7. .7. 2 points before, 2 points after, then get their corresponding F values. We're fine by attendance. This one should be T, not X. Radian. You have to use radian because the T value 0.7. There is no degree symbol. There's no degree symbol, so you have to use radian. Okay, do everyone sign for attendance? Remember, put the f double prime 0.7 on the left. Okay, you have to show what you are what you are approximating now. Okay, attendance, who else? Okay, after you compute for the approximation, you have to find for the percent relative error. Okay, sometimes the formula of percent relative error is not given. Okay, when you are asked to find percent relative error, normally formula is not given. If we know that the relative error, that means we want to compare our approximations with the true value. Okay, true value minus approximation over true value. That is relative error. But because of the percent relative error, that means we need to multiply 100%. Okay, next one, backward difference approximations. Okay, use backward difference approximation. Okay, after forward difference approximation, okay, we use backward difference approximation. According to the question, we need to use these first three methods. Okay, standard difference. Last one. Okay, so if you compare these three of the errors for these three methods, actually the standard gives you the lowest percent relative error. Okay, for those who have done, please proceed to number 2. Also that's the okay, that's been the formula number 4, 5, 6. Okay, you have to find for second derivative. Okay, second derivative. To estimate for this one, okay, step size is 0.1. So you have to choose the correct point. Okay, since points are given. Okay, so we use these three formulas. So if we start with time of accuracy, forward difference approximation. Okay, you need to estimate for F double prime 2.0. With a step size of 0.1. Okay, substitute the values of x and h, then you know which point you use. For numerical differentiation, all these 12 formulas will be given in the appendix. Okay, you don't have to memorize these 12 formulas. Okay, last question. This is a past year question. This is a past year final exam question. Okay, a spring with spring constant K is attached to a mass m kilogram of mass with friction constant B. Okay, it's forced to the right by an external force, and the motion. Okay, motion is governed by this equation. Okay, that means you are given this equation. Okay, now given that the K is 4, M is 1, B is 4. Estimate the external force, this one, for each of the time recorded as in table by using appropriate 3 points difference formula. External force. Not external force. Yeah. We want to estimate this one. Okay, we want to estimate the external force, and this external force is given by this. So do you have any idea how to solve this? You are given this. You are given the MVK values. You want to get this. Okay, this one for each of the time recorded as in this table. That means it wants you to get what is F0. Okay, what is F0.5? F1.0, F1.5. Okay, now we start from this one. To get an F0, when T is 0, that means this one, the Y double prime in 0, right? Y prime also in 0. This is Y in 0. When you need to find for F0.5, that means this is Y double prime 0.5, Y prime 0.5. This is Y 0.5. So how to get the Y prime? This one, we start from this one. How to get a Y double prime 0? You use the second order derivatives formula, right? Yes. To get the value of this. And for this one, to get this value, you need to use the first order derivative formulas. Okay, but forward, backward difference, which one to use? Okay, it depends on the points. When you want to estimate for F0, okay, that's mean here you want to estimate for Y double prime 0, you have to use forward. This one also forward. Y0 is given here too. So when you get these three values, then you will get the F0. Okay. So see, this is the formula. This is the table for the answer. When t is 0, okay, y is 2. For first order numerical differentiation, we use forward difference approximation. Okay, we use forward difference approximation. Then you will get y prime as 0.4. Okay, this is y prime 0. You get 0.4. And for the second order numerical differentiation, this one, you have to use forward difference approximation. You will get 2.4. Okay, then after you substitute this y prime, y double prime, and y value into the formula just now, you will get F0 as 12. Okay, we try to get the answer for this one first. Okay, write out the equation. Okay, your Ft is M is 1. Okay, so y double prime plus B is 4. Okay, B is 4, y prime is E, and your K is 4. Okay, so you have this equation. Okay, this equation. So now when t equals to 0, okay, when t equals to 0, we need to find for this. So this one, we have to use the forward difference approximation. Okay, second order forward difference approximation. Okay, we don't use the high accuracy because, okay, here if you look at the question mentions using an appropriate 3 points difference formula. 3 points. Okay, 3 points. So for second order, okay, for second order, this is 3 points. This one, for second order differentiation, this is 3 points. If you use the high accuracy forward, this is not 3 points. This is 4 points. Okay, so we want to use only the 3 points, okay, and under second order derivative, and we want the forward. So we use this formula to find for this y double prime 0. Okay, so to get a y double prime 0, to get this y double prime 0, okay, we use this f double prime. This one, the first formula, fx minus 2 plus f divided by h squared. Okay, so meaning that you want to get this. Okay, to get a y double prime, this one double prime, we want this one to be 0. So it means we need this. Okay, this one. What is your age? What is your age? Look at the given values. 0.5. Okay, 0.5. 0.5 plus 0, 0.5. Then this is 1.0. 0.5 squared. Okay, then you substitute the values of F0. F0, that means 2. 2 minus 2.5 plus 3.6 divided by 0.25. Okay, so this one you get. You get a 2.4, is it?
Yeah.
0.4. Okay, you get a 2.4, sorry. 2.4. 2.4. Okay, then to get this y prime 0. Y prime 0, that means we need to use the formula of first order. This is 0. Okay, now we look at the formula of the first order. Okay, first order. Okay, now if you look at the first order, you want to use this one or this one. You have to use the first one or the second one. The second one, because this is 3 points. Okay, 3 points. Okay, current is 0. Okay, 0, 0.5, 1.0. Okay, so this should be negative. Okay, 1.0. 3.6 plus 4. 0.9 is 2.5 minus 3 times 2. Okay, divided by 1. This one. Is it 0.4? Okay, so that's mean now you have already got for the case of t equals to 0, your f0 will be this one. Your f0 will be 2.4 plus 4 times 0.4 plus 4 times y0. What is your y0? Y0 is 2. Okay, so this one, what do you get? You get a 12, right? Okay, now you look at this table once again. Okay, so for the case when t equals to 0, your y is 2, y prime is 0.4, y double prime is 2.4. So your ft is 12. So for the case of 0.5, okay, for the case of 0.5, okay, you can either use this forward difference approximation or standard difference approximation. Okay, because we need 3 points. Okay, 3 points, you can only use either forward or standard. Okay, then you will get, so it depends whether you use forward or standard, you will get slightly different values. Okay, so the marking scheme, it will be based on what you choose. Okay, but of course, if we want a better approximation, we will choose standard. Okay, standard. Okay, we will look at which big O notation the accuracy is highest. Okay, because we have already know that, okay, the answer given by the algorithm with a higher accuracy or complexity of algorithm, it will give us a better solution. Okay, so this one, if we want to get a better result, okay, so you can use standard difference approximation. Okay, you can use FCA, but CBA will give you a better approximation. Okay, normally we will choose the best, okay, the one that can give us a better approximation. Okay, so if you use this CDA, you get this one. Okay, this one I will leave it to you to try. Okay, to try. Okay, this is a partial question. Okay, but I think this is the most high, the level of difficulty for this year. Okay, for this one, this year, not this current year. For this question is the most difficult one. Okay, the rest of the past year, okay, actually the question is quite straightforward. Okay, this is the hardest one. Among the past year questions, this is the hardest one. So if you are able to understand the hardest one, the rest is just a peanut. Okay. Okay, so this one I leave it to you to try. Okay, you can try. Can you try to use CDA? This one also you can try use CDA since it gives a better approximation. And the last one, we have no choice but have to use backup. Okay, so we have done this numerical differentiation. Okay, we have done this numerical differentiation. Okay, next class, we will move to a new chapter, which is integration. Okay, integration. So next week, we will move into integration. So today we stop here. And please do not be late for tonight. Okay, do not be late for tonight.